200 newtons is at rest on a slope which makes an angle theta with the horizontal. Draw a diagram and calculate the friction and normal reaction forces if the angle theta is 20 degrees. So we want a slope of approximately 20 degrees with a block sitting on it of weight 200 newtons. There are going to be two further forces acting on the block. The normal reaction force I'm going to label N, and the friction force up the slope I'm going to label F. As we said before, in this particular case, what we want to do is resolve in the set of the pair of planes that are parallel to the slope and perpendicular to the slope. This is because for this particular block, the forces in the direction perpendicular to the block must sum to 0. It doesn't float up above the block or sink into the block. But also for this particular block, because it is at rest, we can say that the forces up the slope and down the slope must also sum to 0. Of course, we should remember that it could be going at a constant speed and this would still be true, but it's not, it's at rest. So we know that the forces in these directions are going to sum to 0. When we come to resolve our vector, then, well, our single vector that we want to resolve, it is the 200 Newton vector that's causing us a problem. I'm going to do it over here at the side. I've got my 200 Newton vector downwards. I'm going to resolve it into two components. The one that is perpendicular to the slope, that one is adjacent to the angle of 20 degrees, and therefore it has a size of 200 cos 20. And the one that's parallel to the slope, so we might choose to draw it here, or we might choose to draw it here. This one being on the opposite side of the triangle has size 200 sine 20. So now, once we've got these two vectors, the rest of our question is straightforward. The size of the normal force must be equal to the component of the weight that's going into the slope, so that the resultant in the perpendicular to slope plane is equal to 0. So if we're writing this strictly in vector notation, we should say 0 is equal to n plus 200 sine 20, cos 20, excuse me. So we're going to write it like this because one of these vectors will be positive in the coordinate system that we've chosen. One of them will be negative in the coordinate system that we've chosen. However, because we're really only dealing with the magnitudes here, I think it's helpful to think of the sum also in terms of the magnitude. So at this point, quite often in physics, we're not very careful about how we write these things down. And we might write something like n is equal to 200 cos 20. Well, strictly that's not true because they're in opposite directions. What we really mean is the magnitude of n is equal to the magnitude of 200 cos 20, but we don't tend to show these signs. So when it's written like this, it's slightly unclear as to whether we're using vector notation or standard scalar notation. So here we're effectively using scalar notation to find the size of n rather than the vector magnitude of n. Of course, the two are the same in this particular case. So 200 cos 20 has a value of 187.9. We've got this 20 degrees, so we're working to two significant figures, so 190 newtons. And equally, the friction force we're going to say is equal in size to 200 sine 20, which gives us a value of 68.4, so we're going to write 68 newtons.